Gang. So today is your day. Sorry, I'm running a few minutes late getting in here. Today is your day. We can work on whatever you guys want to work on. I think we should solve lots of problems. And of course, Friday is the test. The test is going to run the same way exam 1 did. So if you need a refresher on those protocols, please take a look at the announcements that I posted leading up to exam 1 that explains exactly how to do everything. And for now, let's just dive in. Okay. So we want 14 and 18 from the study guide, 39 from homework 9. So I'm going to start with the homework 9 stuff. Sorry, this is what I was doing a minute ago. Where are you? Homework 9, 39. 30, okay, I see more stuff coming in. 30, 39, and 44 from homework 9. So let's start with number 30. Oh, this is good. Yeah. So I'll write this down. That's from 1 to infinity. That's abs, convergent, conditionally convergent, divergent. Okay. So we want to classify the sum, focus, sigma, n from 1 to infinity. Focus, you fuck. Sine of n over 6 to the n as absolutely convergent, conditionally convergent, or divergent. First thing to observe, this is not a series of positive terms. An here is the sine of n over 6 to the n is not always positive. Why? Because like, sure, sine of 0, 1, 2, 3, those are positive, but I think sine of 4 is negative because 4 is a little bigger than pi. So this guy goes like positive, 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 negative, 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 positive, 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 negative, negative, negative. So it's also not alternating. Which means that most of the stuff that we learned in the early sections of chapter 11 don't apply, right? The tests that we learned there required that the ANs be positive. These are not positive. And then 11.5 is only about alternating series. Those are series that go plus, minus, plus, minus. This guy goes plus, 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 minus, 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 plus, 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 minus, minus, minus. So it's not any of that. These are strong hints that we should consider attacking the absolute value series instead. So, however, sigma n from 1 to infinity, absolute value of sine n over 6 to the n is a series with positive terms. So to this series, I could apply whatever I want. If everything was positive here, limit comparison test would be an option, but not necessarily the best option. Because the sine n piece here wants to bounce back and forth, which makes the limit that you would need for limit comparison test a little bit challenging. So what I'm showing here, I definitely believe to be the best approach. The best approach is, because these aren't all positive and not alternating, replace the inside with its absolute value. If this series converges, then the original series converges absolutely. And that would solve the problem. And the convergence of this series is actually pretty easy to get using a direct comparison. So here, I would begin with the fact that the absolute value of the sine of n is always greater than or equal to 0 and less than or equal to 1. Which means if I divide through by 6 to the n, I get this. And my series, if you split up the absolute value, is the series with the absolute value of sine n divided by 6 to the n, because the absolute value of 6 to the n is just 6 to the n. Is this series. So by this inequality, I would say moreover, or also, or whatever, sigma n from 1 to infinity 1 over 6 to the n, that's the same as sigma n from 1 to infinity 1/6 to the n, is a geometric series with the absolute value of r being the absolute value of 1/6, which is 1/6, which is less than 1. So this series converges. Thus, by the inequality star and the direct comparison test, sigma absolute value sine n over 6 to the n converges. Which means the given series, sigma n from 1 to infinity sine n over 6 to the n, converges absolutely. So a limit comparison here would be hard. If you choose the bn's so that the limit is easy to calculate, then the series sigma bn would have a sine n in it, which means it would be hard to work with on its own. And if you choose the bn so that the series sigma bn is easy to work with, then the limit in the limit comparison test would be hard to work with. So I'm not aware of a way to make this work with limit comparison test. But if you take absolute values inside and then use a direct comparison, this becomes easy. And the hint to do that is that the numerator is bounded, right? Sine n is always bounded between -1 and 1. So his absolute value is always bounded between 0 and 1. So that's the strong hint that this series behaves a lot like the 1 over 6 to the n series. And then you just have to remember the technical details to make it work. You can't apply DCT to this series directly because it's not a series of positive terms. You can't apply LCT or integral test or any of that shit directly. So your first step has to be to look at this series, the series with the absolute values inside. Since that series is a series with positive terms, you can structure your DCT. And then the series that you're comparing against, the 1 over 6 to the n series, 1 over 6 to the n is the same as 1/6 to the n, because the 1 doesn't care if you raise it to the nth power. Since that series is a convergent geometric series, because the absolute value of his common ratio is less than 1, this series has to converge. Since this series converges, the original series converges absolutely. So I think if we're going in order, 37 is next. Ah. So if you watch the video I posted Monday night, so check this out. If you didn't see this, that's understandable. If you come to the announcements for our class, I posted a link here, some extra series problems. This is actually one of those problems. I think it's like the third one that I do. Yeah, this is it. It's actually paused right here. So I was rewatching it the other night. Where is it? Come on. This player doesn't want to work. Yeah, so I posted a handful of extra series problems. And the first one you see is classify n factorial over n to the n as absolutely convergent, conditionally convergent, or divergent. So take a look at that video for the solution to this problem. I run TFD. The TFD limit here is 0. It's not super exciting. And then I run the ratio test. The ratio test limit here is fun. It's funky. I can show you, there's a different way to do the limit there than I did in this video, so maybe it wouldn't hurt for me to run back through this one more time. So let's do it. I'll flip back to the dot cam. Sigma n factorial over n to the n summed from 1 to infinity. Let's use the ratio test because there are some factorials. L, as always, is the limit as n goes to infinity, abs an plus 1 over an. And you do have to be careful with this. That's the limit as n goes to infinity of the absolute value of n plus 1 factorial divided by n plus 1 raised to the power of n plus 1. So that's an plus 1, right? This right here is an plus 1. Everywhere there's an n, you have to swap for n plus 1. And most people tend to forget one of these. Another common mistake is forgetting to put the parentheses here, or forgetting to put parentheses here. So make sure you don't do that. Then I'll multiply by the reciprocal of an, because that's the same as dividing by an. So that's n to the n over n factorial, close absolute value. Now I write everything out. Everything here is positive, so I'm going to ditch the absolute values. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1, times n to the n is just n to the n. And then downstairs, I have n plus 1 to the n plus 1. That's n plus 1 to the n times n plus 1 to the 1. And then n factorial is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. So if you start looking around here for things that cancel, I've got this n factorial product here, and I've got that same stuff showing up here inside of n plus 1 factorial. So these all cancel with these. Everything from n down to 1 cancels there. And what I'm left with is the limit as n goes to infinity. Upstairs I have n plus 1 times n to the n. And downstairs I have n plus 1 to the n times n plus 1. And the n plus 1s cancel. So there's an awful lot of cancellation here. At the end of the day, I have lim n to infinity, n to the n over n plus 1 to the n. And both the top and bottom are going to infinity as n goes to infinity. It's not an easy thing to L'Hopital though, because the derivative of n to the n is horrendous. n plus 1 to the 1 came from n plus 1 to the n plus 1. So n plus 1 raised to the power of n plus 1 is n plus 1 raised to the power of n times n plus 1 raised to the power of 1. Yeah, it's a little sneaky. Yep, lots of exponent rules. So while this limit appears to be a good candidate for L'Hopital's rule, the derivatives of the top and bottom are horrendous because both the base and the exponent are variable, right? You may remember the derivative of x to the x from Calc 1. That's something you learn how to do with logarithmic differentiation. It is not at all nice. You can't use the power rule. You can't use the normal exponential chain rule stuff. Neither of them work because neither the base nor the power is constant. The same is true in the denominator. So I don't want to try to jump in with L'Hopital's rule, even though I could. What's better is to do some algebra. Since the top and bottom are both being raised to the same power, that's the same as the top over the bottom all being raised to that power. Yeah, exactly. Yep. So what Ryan said in chat is perfect. There's two nice ways to handle this limit. What I'm going to do right now is exactly what Ryan said. So I'm going to now take reciprocals inside. This is the limit as n goes to infinity of n plus 1 over n all raised to the negative n. So I flip the inside and make the power negative. And then I split up the inside. I do this because I want to split up that fraction inside to make this look like my e to the ab limit. N over n is 1. So n plus 1 over n is 1 plus 1 over n, all raised to the negative nth power. And this is e to the 1 times negative 1 by our e to the ab limit. All right, the limit is lim n to infinity 1 plus a over n raised to the bn equals e to the ab. So L is e to the negative 1 or 1 over e, which is definitely less than 1. So the series converges absolutely by the ratio test. That's the game. Now, if you look in the video that I just referenced, when I get to this point, I do long division inside instead of taking reciprocals, and the limit comes out the same, of course, but the work is a little bit different and it requires a little substitution. I don't think you'll have a hard time with either one, but I do feel like this approach is the one that's normally taught. So I'm happy to go through this here with you guys. Questions on this problem? The hint to use the ratio test is the n factorial. Factorial or factorial-like stuff always hints strongly at the ratio test. And then the trick is to write everything out. You write out the factorials and the powers. And then you'll see lots of cancellation. And then what's left is an indeterminate form of the type 1 to the infinity. And the only other place we've seen that particular indeterminate form, 1 to the infinity, is in this e to the ab limit. So that should start making us think of the e to the ab limit. So then I start trying to massage this algebraically to look like that. And the first thing I realize is that I need a 1. I need like 1 plus something. So if this was the reciprocal, it would be easier to write that way. So I take reciprocals. That makes the power negative. And then I split up the fraction. And now I'm in that nice 1 plus a over n raised to the bn form. So I know that this will be e to the a, which is 1 times b, which is negative 1. So I get e to the 1 times negative 1, which is e to the negative 1, which is 1 over e. Since E is like 2.7, this is like 1 over 2.7, definitely smaller than 1. So the series converges absolutely by the ratio test. Okay, moving along. I'm trying to see where everything is coming from. So what have we done so far? That was 37. 39 was also requested from that homework. 31 and 33. What's 31 and 33 look like? 31 is not bad. I'll do 31 real quick. If we can even fit that on the page here. So this is homework 931. I'm not going to write all the words. We're summing from 1 to infinity, n over 9 to the n. And they asked us to use the ratio test. So we will. L here is always the limit as n goes to infinity. Absolute value an plus 1 over an is the limit as n goes to infinity. Absolute value of n plus 1 over 9 to the n plus 1 times. I'll multiply by the reciprocal of an, which is 9 to the n over n. So that's the limit as n goes to infinity. I'm just going to shuffle the terms around. N plus 1 over n times 9 to the n over 9 to the n plus 1. Little bit more algebra. The n plus 1 over n piece I'll leave alone, but here I've got n copies of 9 upstairs and n plus 1 copies of 9 downstairs. That's just 1/9. No calculus, just algebra. And then finally, n plus 1 over n goes to 1. You can renormalize if you want. But we should be getting good at seeing this. This is 1 plus 1 over n divided by 1 times 1/9. So as n goes to infinity, 1 over n goes to 0. So this is the absolute value of 1 plus 0 over 1 times 1 over 9, which is 1 times 1 over 9, which is 1 over 9, which is less than 1. So the series converges absolutely by the ratio test. So this one's not bad. 33. '33 is a little bit more exciting, so I will go through that one. And then we're going to move to study guide problems. Where did it go? Disappear? 33 had a negative 3 to the n over 2n plus 1 factorial, right? Yeah. I reloaded the page, so it says negative 7 to the n now over 2n plus 1 factorial, and we're summing from 0 this time. Doesn't make a difference. But this is, again, a ratio test thing. L is the limit as n goes to infinity, abs an plus 1 over an. Remember, I always suggest that you write down the pieces from the test you're going to use without the stuff plugged in. That way I can give you partial credit for the stuff that you do know, even if you make a mistake in the next step. This is going to be the limit as n goes to infinity of the absolute value of negative 7 to the n plus 1 over parentheses 2, parentheses n plus 1, close parentheses plus 1, close parentheses factorial, like that. That's an plus 1. Got to be real careful. If you forget these parentheses, you'll get the wrong thing. And then I multiply by the reciprocal of an, which is 2n plus 1 factorial over negative 7 to the n. Here, not everything is positive. This is actually an alternating series. You could use the alternating series test if you wanted to, but again, because of the factorial downstairs, I'm inclined to say ratio test. Just like we did in the last problem, I'm going to shuffle these around and put the like terms together, or the similar things together. So I'll put this with this, and this with this. Downstairs here, 2n plus 1 is 2n plus 2 plus 1 is 2n plus 3 factorial. So I'll have lim n to infinity, absolute value, negative 7 to the n plus 1 over negative 7 to the n times 2n plus 1 factorial over 2n plus 3 factorial. And we remember that a larger factorial always contains a smaller factorial. This is the product of all the numbers less than or equal to 2n plus 3. This is the product of all the numbers less than or equal to 2n plus 1. So this whole thing is going to cancel with this whole thing. Similarly here, I've got n plus 1 copies of negative 7 upstairs and n copies of negative 7 downstairs. So I have one more copy upstairs than I have downstairs. So I'll get lim n to infinity, absolute value of negative 7. That's the first piece. And then the other piece is 2n plus 1 times 2n times 2n minus 1, all the way down to 3 times 2 times 1. That's 2n plus 1 factorial. 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, all the way down to 3 times 2 times 1. In other words, 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So the 2n plus 1 factorial from the top cancels completely with the trailing terms from 2n plus 3 factorial. And you get lim n to infinity, absolute value of negative 7 times 1 over 2n plus 3 times 2n plus 2. The negative 7 is constant. He's inside the absolute value. You could pop him out as a 7 if you wanted. So if you're feeling fancy, you could write this as 7 times lim n to infinity, 1 over 2n plus 3 times 2n plus 2. However you get there, the limit here is going to be 0. This is 7 times 1 over infinity, which is 0. So L equals 0 is less than 1. Therefore, the series converges absolutely. By the ratio test. So please be mindful of how you are writing things. Be very careful with your parentheses. And when you encounter a weird factorial, just write the thing out. If you're not sure what else to do, write the whole thing out. Write it out until your hand gets sore, and then look for what cancels. Watch for patterns. All right. So the next move is going to be stuff from the study guide. I see we want 14, 18, There's some stuff from homework 8 we wanted, 15 and 20. I'll go back to those if I have time. 18 from the study guide has been requested twice, so let me move to the study guide next. 6, 14, and 18. So now remember what factorials do. The factorial of anything is that thing times that thing minus 1 times that thing minus 2, all the way down to 3 times 2 times 1. So the factorial of 2n plus 1 is that thing, 2n plus 1, times that thing minus 1, which is 2n, times that thing minus 2, which is 2n minus 1, all the way down to 3 times 2 times 1. So the factorial of anything is what you get when you multiply that thing times that thing minus 1 times that thing minus 2, and just keep going until you get to 1. So in the study guide, I'll start with 6. 6 is straightforward and fast. Find an where an, the sequence, has terms 1, 1/3, 1/5, 1/7, 1/9, and so on. Assume n begins at n equals 1. Okay. So what I see here is 1 over 1, 1 over 3, 1 over 5, 1 over 7, 1 over 9. This is the reciprocal of all the odd numbers. So your generic odd number here you can write them as 2n plus 1 or 2n minus 1, right? An odd number is always off from an even number by 1. An even number is always a multiple of 2. If I plug n equals 1 in here, I get 3. If I plug n equals 1 in here, I get 1. So if I want to make my sequence start at n equals 1, I should take the reciprocal of this. So an here is 1 over 2n minus 1. Right? This is 1 over 2 minus 1, 1 over 4 minus 1, 1 over 5 minus 1. Sorry. 1 over 2 minus 1, 1 over 4 minus 1, 1 over 6 minus 1, 1 over 8 minus 1. It's 1 over 2n minus 1. So that's it. I think that's everything for number 6. They just wanted the formula. Yeah. So our next study guide problem, I see 2 has been requested there. 14, 18 has been asked for a couple times, right? Let's do 18 to make sure we get to it. Ah, good shit. Again, I'm just going to write down the series. We know what we want to do. We want to classify it according to its convergence. It's the -1 to the n times n over the square root of n cubed plus 2 series. So what do we see here? It's definitely not geometric or telescoping. Doesn't look anything like those. It is alternating, so we could try the alternating series test. But if I imagine that it's not alternating, if I imagine that this piece wasn't here, then I would have n over the square root of n cubed plus 2. Let me show you a little something. N over the square root of n cubed plus 2, if I imagine n is really friggin' big, then n cubed is so much bigger than 2 that I don't really give a shit about the 2. This is pretty much the same as n over the square root of n cubed for large n. The square root of n cubed is n to the 3/2. So this is like n to the 1 over n to the 3/2, which is like 1 over, which is actually equal to 1 over n to the 1/2. So in other words, this is a lot like the 1 over root n series. Ratio test is actually going to be inconclusive on this. Any series where you have an algebraic function of n, meaning like a rational function, polynomial function, or rational function including some square roots and stuff, ratio test is inconclusive on all of those. So the only time you want to use the ratio test is if you have like factorials or something that looks geometric-ish, like 6 to the n or 5 to the n. You need faster growing stuff. The ratio test isn't sensitive to slow growing or slow decaying stuff. It's only sensitive to really fast growing and fast decaying stuff. Since this is an algebraic function of n, it doesn't grow or decay, no parts of it grow or decay fast enough for the ratio test to be able to pick up on what's going on here. But this observation is hugely useful. And you should play this game in the back of your head with pretty much every series you encounter. So this guy, my bn's, if you want to think of this as an alternating series, this is a lot like the alternating 1 over root n series. So yeah, it's kind of like an alternating piece series. It's not a piece series because it's alternating and also it's got all this other shit going on. But my guy is very similar to a piece series. I can't use limit comparison test right away because of the non-positivity. Remember, limit comparison, direct comparison, all of those require positive terms. So I'm going to do two things here. First, I'm going to look at the absolute value series. And I'm going to show that the absolute value series diverges. That's going to require a limit comparison. And then I'm going to use the alternating series test to show that the series is convergent. The AST work here is actually going to be really unpleasant because showing that this sequence is decreasing is really unpleasant. I don't, oh, maybe we could sneak away with something cheaper. Nah, nope, all right, it just kind of sucks. I definitely don't want to do the integral test. The thing that makes AST suck is the same thing that makes the integral test suck. It's trying to show that this is decreasing. That's unpleasant. And you'd have to do that for the integral test also. And the integral test doesn't apply because this isn't positive because the -1 to the n. Nah, bigger denominator does not mean increasing. It means smaller than 1, right? N plus 1, or n divided by n plus 1 is not always decreasing, but n plus 1 is always bigger than n. So bigger denominator does not mean decreasing. Faster growing denominator means decreasing. And here, I don't think you'll see that right away. Right. So let's jump in. First, consider the absolute value series, which is the sum from 1 to infinity, absolute value, -1 to the n over the square root of n cubed plus 2. This guy is the sum from 1 to infinity, absolute value of -1 to the n times absolute value of n over absolute value square root n cubed plus 2, which is equal to, the absolute value of -1 to the n is just 1. Absolute value of n is just n. The absolute value of that square root is just that square root. So the absolute value series is this. And unfortunately, this does not fall to direct comparison. This is a little bit smaller. So when I say this shaky equivalence, the truth is that this guy is a teensy weensy bit smaller than this guy. And since the sum of these diverge, DCT isn't helpful. So yep, we need limit comparison. So I'm going to apply the limit comparison test to this series. I'm going to pick Bn to be 1 over root n, because I know that that's my basic behavior, is like 1 over root n, and calculate lim n to infinity this guy over that guy. Because the inequality points the wrong way for direct comparison. My guy, this thing, is a little bit smaller than this thing, not a little bit bigger. If this was a little bit bigger than this, then I could get the divergence of this series using DCT. But unfortunately, this is a little bit smaller than this. And being smaller than a guy whose sum diverges doesn't tell us anything. So if I mash this together, flip and multiply, I get n to the 3 halves over the square root of n cubed plus 2. N to the 3 halves, that's the same thing as the square root of n cubed. So I have the square root of n cubed over the square root of n cubed plus 2. The limit comparison here is really not bad. I write that as a single big square root with n cubed over n cubed plus 2 inside. And then n cubed over n cubed plus 2, the inside of this square root goes to 1. You could renormalize if you want to, but again, we should be good at this stuff by now. We should be able to say, oh, well, the power of the top and the bottom here are the same. The lead coefficients are 1. Like right away, I recognize, yeah, the inside goes to 1. So this is the square root of 1, which is 1. So the number C from the limit comparison test is 1. Since C equals 1 is positive and finite, sigma this thing, n over square root of n cubed plus 2 converges or diverges together with sigma 1 over square root n, which is sigma 1 over n to the 1/2, which is a divergent P series, because P is equal to 1/2, which is not bigger than 1. Therefore, the series n over square root n cubed plus 2 diverges also. Hence, my series, the original series, does not converge absolutely. But now it still remains whether my series diverges or converges conditionally. It's going to turn out that this series converges conditionally because it's like the alternating 1 over root n series. But in order to show that, I need to run AST. The AST work here is kind of a pain in the ass, but we'll do our best. So finish things up. We use the alternating series test. here my bn's are n over the square root of n cubed plus 2. Remember, AST calls bn the non-alternating part of your series. And I need to know, is the sequence bn decreasing? And is the limit, as n goes to infinity, of the bn's equal to 0? The answer to the second question is a clear yes. So let's knock him out. Lim n to infinity, n over the square root of n cubed plus 2. I can divide top and bottom by n. The numerator will become 1, and the denominator is the square root of n cubed plus 2 times 1 over n. And that 1 over n I can treat as the square root of 1 over n squared. So this is 1 over the square root of n cubed plus 2 times the square root of 1 over n squared. And then I can mash the two square roots downstairs together, distribute. And when I do that, n cubed times 1 over n squared is n, plus 2 times 1 over n squared is 2 over n squared. So in the limit, this is 1 over the square root of infinity plus 0, which is 1 over infinity, which is 0. So yes, lim n to infinity bn equals 0. But are they decreasing? And the decreasing is important. I don't want to do it. I really don't, but we have to. So the move here is going to be to take the derivative of the corresponding function So we consider the corresponding function, that is x over the square root of x cubed plus 2. And we show that f prime is negative eventually. Doesn't always need to be negative, but there needs to be some point such that from that point on, f primed is negative, because that would mean there is some number n such that beyond that n, the bn's are always decreasing, which is what AST requires. F primed here is a bit of a nightmare. The downstairs is just going to be x cubed plus 2 because I squared the denominator in my quotient rule. The upstairs is going to be the bottom times the derivative of the top, which is just the bottom, minus the top times the derivative of the bottom, which looks like that. It's a chain rule derivative. Your goal, whether you are willing to accept it or not, is to figure out where this son of a bitch is positive and negative. I recommend thinking of it like this. This is x cubed plus 2 to the positive 1/2 minus 3/2 x cubed times x cubed plus 2 to the negative 1/2 all over x cubed plus 2. So I combined all the like terms here. The 1/2 and the 3 make 3/2. The x and the x squared make x cubed. And this is this. You may remember a tried and true trick. Yeah, it's hard to overstate just how messy some of this stuff can get. Don't just take the L on this problem. The thing to do on this, if this problem showed up on a test, the thing to do is, boom, right here. This. This line told me everything about the series. Let me be clear about that. From this line, I can conclude this is approximately the alternating 1/√n series. And immediately I know it's conditionally convergent. All right, let me be clear about that. No need to go through all this bullshit on a multiple choice version of this question. Because this thing is approximately this thing, my series is approximately this series. 1/√n, without the alternating piece, we know to diverge as a piece series. 1/√n with the alternating piece, we know to converge as an alternating series. The intuition comes immediately from this. That's why I showed you this. But the details are a little fucking hairy. Now we're almost there, so be brave. The thing to do here is to factor out this guy. This is the thing that sucks. And if you factor out this guy will get a power of +1. So I am going to force factor x cubed plus 2 to the -1/2. And what will be left upstairs is x cubed plus 2 to the 1/2 minus -1/2 is x cubed plus 2 to the 1. And then you have minus 3/2 x cubed. All of this is still over, x cubed plus 2. What do we need to know? Show the detail of the written response question. Yeah, if this was a free response question, you would need to show all of these details. Now, I'm not going to beat you to death with a free response question like this on the test, but it's important that you know how to handle things like this. Something like this could definitely show up as a multiple choice or true-false question, and for those, the very first line is literally all you need. But if it were a free response question, then you would need to run through the details of the convergence tests. If on a free response question you gave me an answer that was just based on this, I'd give you like half credit. If it were a true-false multiple choice question, that's the appropriate domain for this sort of thing on a test. Unless it were like the final and it was one of like 5 questions and you had an hour to do it. Almost done, let's be brave. I can move this piece downstairs and I get x cubed plus 2 to the 3/2. Upstairs, what's left is x cubed minus 3/2 x cubed. That's minus 1/2 x cubed and a plus 2. Force factor a 2. Force factor a 2, and you get negative x cubed plus 4 over x cubed plus 2 to the 3/2. This is all derivative work and algebra work that you've done in Calc 1. We shouldn't have a horrible time getting f primed into this form. I'm a realist. I know that in the actual exam setting, maybe a quarter of people would get here. But from the end behavior, you can deduce that this guy wins, right? The denominator is positive. The numerator is negative x cubed plus 4 times a positive constant. So the end behavior of negative x cubed plus 2 is as x goes to negative infinity, y goes to positive infinity, and as x goes to positive infinity, y goes to negative infinity. So f primed of x is eventually negative. Right? All the things that you learned in Calc 1 are relevant. End behavior, factoring, derivatives, limits, all that stuff. The sneaky bit is here. I am force factoring this. So when you have an expression like this numerator, where you've got these fractional powers and some of them are negative, the best way to clean that up is to force factor the most negative powered piece out. So I force factor this piece out. What will be left here is 3/2 x cubed. What will be left here is this divided by this. Remember, factoring is dividing. If I divide x cubed plus 2 to the 1/2 by x cubed plus 2 to the negative 1/2, then what I get is x cubed plus 2 to the 1/2 minus negative 1/2 is x cubed plus 2 to the 1. Check it. Distribute this back through. Some shit to the negative 1/2 times that shit to the 1 is that shit to the positive 1/2. It works. So this is a trick we usually learn in Calc 1. If you haven't seen it before, I'm happy to be the one to show it to you. You're one of today's lucky 10,000. Congratulations. But yeah, if you need to factor some big sloppy mess where you've got a common base raised to nasty powers, and some of those powers are negative, you grab the piece that has the most negative power and you force factor it out. That will leave only positive power stuff behind. That's the design. And because the way derivatives work, where you're usually subtracting 1 from the power to go from here to here, when you divide, usually you'll get a whole number here. I had a problem with my Calc 1 class where this actually came out to a ratio, but it was still positive. Right, yeah, exactly. Simon nailed it, because the negative exponent is the same as 1 over that shit. You can get there by having a common denominator too. I could write this as 1 over the square root of x cubed plus 2, and this as the square root of x cubed plus 2. Then my common denominator would require multiplying by the square root of x cubed plus 2 over the square root of x cubed plus 2. And the 2 square roots upstairs would give me the first power. It just takes longer if you write it that way. Anyway, f prime is eventually negative. Therefore, the sequence Bn is eventually decreasing. Therefore, by AST, the series sigma n from 1 to infinity negative 1 to the n over the square root of n cubed plus 2 converges. But it did not converge absolutely. Same question as Morgan. What did Morgan ask up there? How did I factor to the last step? Here to here, I force factored, oh, sorry, I force factored a 1/2. Sorry, I wrote it as a 2. This should be a 1/2. Sorry. So I force factored out a 1/2. Negative 1/2 x cubed divided by 1/2 is negative x cubed. 2 divided by 1/2 is 4. Yeah, so I miswrote that. This shouldn't have been a 2. This should be a 1/2. My bad. Good catch. All of it. Yeah. This is a minimal solution. I hate to say that, but that's the truth. This is a long problem. There's like 10 problems in the study guide, right? So there's 1 or 2 long ones. This is definitely one of the long ones. I have to put you through hell. I got to do it. It's Calc 2. I'm not trying to put you through hell. I love you guys. I don't want to hurt you. But these are the skills that we're testing for. This is, you know, you run a mile to make sure you can run 100 meters. This is your mile. I'm sorry. Please don't feel hurt. We all have to go through this, okay? I promise you, I went through this. Everyone you know who's been through Calc 2 went through this. Remember, this is your guiding light. This is what tells you everything you actually need to know. From this line, I knew that my series converged conditionally. That it converged, but it would not converge absolutely. So you know where everything is going. It's so much easier to go on a long walk when you can see the destination, right? From this line, you can see the destination. So then it's just a matter of grinding out the details. And most of the details really aren't that bad. The only unpleasant thing is this derivative work. But you did stuff like this in Calc 1. I know you did. I mean, I sure as shit hope you did. So we take this derivative, and normally you would have to then factor the numerator. Yeah. I appreciate the Fallout reference. Sad acoustic guitar, yeah. Can you assume that this is bigger than the numerator? Well, it is bigger than the numerator, but that doesn't mean that you're decreasing, right? Example. Here, the denominator is bigger than the numerator. But this is actually a decreasing function. This is n plus 1 minus 1 over n plus 1, which is 1 minus 1 over n plus 1. This is a decreasing function. So not every function which has a denominator larger than a numerator is decreasing. Doesn't even mean it's going to 0. Actually just means that each term is less than 1. So the bottom being bigger than the top does not mean you're decreasing. Sorry, this is I said decreasing. This is an increasing function. All right, you start at 1 and then you subtract less and less. So this is an increasing function, but the denominator is bigger than the numerator. So having a larger denominator does not mean that you are decreasing. It just means that you're smaller than 1. Peter is getting closer to an argument that is of the style you guys want to keep making. If the power of the denominator is larger than the power of the numerator, it is true that you will be eventually decreasing. But even that argument really doesn't hold water here, because you can't really talk about a power of the denominator, because the denominator isn't a polynomial. Growth rates will not prove eventually increasing or decreasing, unfortunately. Growth rates, and I went through this in detail with Fernando in office hours Monday. Growth rates would show you that this guy has limit 0, but it is possible to have limit 0 and not be decreasing. It's even possible to be always positive and have limit 0, but not be eventually decreasing. And my favorite example of stuff like that is something like this. So if I start up here and I have limit 0, you might think that that means I have to be decreasing, but what about this? This guy sure as shit is not decreasing, right? Decreasing, increasing, decreasing, increasing, decreasing, increasing. He changes all the time. And as long as these waves get smaller and smaller, but I keep trending down, I will have limit 0. Dalton's thinking is pretty good. And that's the sort of thing that led me to write down that intuitive statement with which we began. But I can't say that the power of the denominator is 3/2 because it's not. It's very similar to something who has power 3/2, but the +2 messes it up. So that I would be happy to go through all of the little analytical details with you guys, but for the purposes of today and this review, I will ask you to take my word that the cleanest, fastest way to actually prove, beyond the shadow of a doubt, that the sequence is eventually decreasing is precisely this work. All right, it's 1, 2, 3 lines. It's not that bad. You got to be careful with your algebra. You got to know your calculus. There's not a lot of room for mistakes, but it's really not that bad. Everything you guys have said in chat is great for developing intuition, but it is not a proof. Yeah, we can look at this derivative more carefully. So this is the bottom times the derivative of the top. The derivative of the top is the derivative of x is 1. So 1 times the bottom minus the top times the derivative of the bottom. So to get the derivative of the bottom, I need to prime x cubed plus 2 to the 1/2. That's a chain rule derivative. That's 1/2 times x cubed plus 2 to the negative 1/2. There I'm differentiating the outer power. So I bring the power down and decrease the power by 1. And then I multiply by the derivative of the inside. The derivative of x cubed plus 1 is 3x squared. So this piece is the derivative of the bottom. So the top times the derivative of the bottom is this. So that's your low d high minus high d low. and then the square of the bottom. That's the square of the square root of x cubed plus 2. It's just x cubed plus 2. So yeah, it's low d high minus high d low. That's the quotient rule. So it's a little bit nasty. End behavior. So remember, if you have a polynomial, this is all about the parity of the power and the sign of the lead coefficient. Because the lead coefficient here is negative and the degree is odd, I know that his end behavior is the same as the end behavior of negative x cubed. So he could do all sorts of weird shit in between here, but he's got to go up on the left and down on the right, because this is an odd power. Odd power means that these arrows will point in opposite directions, either up on the left, down on the right, or down on the left, up on the right. And then the negative here tells me that it is going to be up on the left and down on the right, just like negative x cubed. You could say that the lead coefficient is negative 1/2 if you want to think about it from this perspective, but that's still a negative lead coefficient, odd degree. So whether you think of it from this line or from this line is up to you. I like to do this because I like to see if my numerator factors more nicely. Where did I pull? Yes, end behavior here is coming just from the numerator. The denominator is positive. As I plug in bigger and bigger numbers for x, I know that this denominator is positive. I'm not worried about him. Where did I pull the negative x cubed plus 2 from? I don't see, so I've got a negative 1/2 x cubed plus 2 here, and that just came from combining like terms here. So that's x cubed minus 3/2 x cubed is negative 1/2 x cubed. Remember my goal. My goal is to show that f primed is eventually negative. So yeah, Simon, it would be the same. If the numerator was in the end positive and the denominator was in the end negative, then I could still conclude that f primed is eventually negative, and it would work out the same. Yep. So my task here is to determine whether this thing, for very, very large values of x, is negative and stays negative. All right. So I know that's a lot of time on this one problem. I don't want to burn a whole lot more time on this problem. And I would like to again remind you that really everything we needed to know what's going on, we got very, very quickly. From this, I knew that my series converged conditionally. But we have to run through the convergence tests to prove it. And in this portion of this class, Calc 2 is largely about getting comfy with what's called mathematical rigor. Right? Getting to a place where you can be fucking certain. No one can argue with you. That's what theorems are for. Theorems are proof beyond argument. Right? Proof from first principles, from axioms. And that's where we need to be, because infinities can be so friggin' weird. Your intuition doesn't work. It works some of the time, it works most of the time, but it is not a guarantee. So I knew that my series was conditionally convergent because I knew that this piece is very much like this, which means my series, which contains that piece, is very similar to what I would get with my series replaced by this. And this guy, from your homework problems, we should know is a conditionally convergent series. It's an alternating p series where p is between 0 and 1. So he doesn't converge absolutely because the power down here is not bigger than 1, but he does converge because this piece does go to 0 monotonically. Okay, so problems in your homework that you can look at to shore up those concepts exist. They are, I did some of them in office hours yesterday. I think they're the late ones, the ones that involve p's, like what value of p does the blah, blah, blah. Here you go. If you want to get more comfy with the concepts I use to say that this guy is conditionally convergent, come back to 22 from the homework that I opened up last week. What you'll discover is that an alternating p series, which is what this is, it alternates because of the -1 to the stuff. And it's not, I mean, calling it a p-series is a little bit disingenuous, but it's 1 over a power of n. It just happens to alternate. These will converge anytime the power down here is positive. That's what you're meant to discover here. So alternating p-series, series of the form, let's write this down. Sigma negative 1 to the n, 1 over n to the p, converge absolutely if p is bigger than 1, converge conditionally if p is between 0 and 1, less than or equal to 1, and diverge if p is less than 0. And it doesn't matter if this is an n-1 or whatever, it's alternating p-series. So the alternatingness allows them to converge even if p is between 0 and 1. If p is bigger than 1, then when you take absolute values, you get a convergent p-series. If p is between 0 and 1 and you take absolute values, you get a divergent p-series. And if p is negative, this thing fails the test for divergence. So this is a good thing to know. All right, let's move on. What did we just do? What's in the chat here? I did appreciate the follow reference. That was cute. 2 from the study guide, 18 from the study guide, 23. All right. I haven't played Fallout New Vegas yet. I played a tiny little bit of it way back in the day, but I'm actually definitely interested in it. I will get there. I played Fallout 4 last year, and it pretty much ate up my life for about 6 months. So I'm afraid to touch New Vegas, honestly. 2 and 18 we haven't looked at yet. I'm holding out hope for Cyberpunk. If that's as good as it's supposed to be, then I think that will be my next big time crunch. Next big video game time crunch. Okay. Let's come back. We wanted to look at numbers 2 from the study guide, 23 from the study guide, 18. What was 18? 18 is the one we just did. Let's look at 2 and 3. We haven't talked a whole lot about integrals like this. I expect that it is. 14. All right. We got just enough time to do maybe 2 more, so I'm going to go through these somewhat quickly. Study guide 2, problem 2. I probably will play New Vegas at some point in the not too distant future. That's the integral from somewhere to infinity, e to the negative 1 over x squared. So mine has 8 to infinity, e to the negative 1 over x divided by x squared dx. This is a type 1 integral. I haven't heard about that, no, but I'm in favor of banning those disposables because they're so friggin' wasteful. Our dumps are filling up with lithium batteries, and that is a horrible thing for the environment. So ban them, get rid of them, please. I write this as the limit as r goes to infinity, integral 8 to r, because it is a type 1 integral. And then I'm also going to rewrite my integrand. That's e to the negative 1 over x times 1 over x squared dx, because I see a substitution coming. If I sub for 1 over x, then dz is negative 1 over x squared. 8 will go to 1/8, and r will go to 1 over r. So this becomes the limit as r goes to infinity, integral 1/8 to 1 over r, e to the negative z times negative 1 dz. 1 over x squared is negative 1 times dz. Sorry, there should be a dx here. All right. So I can pop out my negative. Negative lim r to infinity, integral 1/8 to 1 over r, e to the negative z dz. I'll get another negative from my antiderivative. That will cancel with this negative. So I just get e to the negative z evaluated from 1/8 to 1 over r. And I should have my limit out front, lim r to infinity. So this negative is eaten up by the negative from the antiderivative. Then I evaluate lim r to infinity, e to the negative 1 over r minus e to the negative 1 over 8. As r goes to infinity, 1 over r goes to 0. So this is e to the 0 minus e to the negative 1/8, which is 1 minus e to the negative 1/8. So the integral 8 to infinity e to the negative 1 over x divided by x squared dx converges to 1 minus e to the negative 1/8. All right. 14 was requested also. I will take a look at 14 and then I am going to have to end for the day. Don't forget the negative from earlier. The negatives got soaked up. This negative gets soaked up by another negative from this antiderivative. When I antiderive this, if you want to, you can think of it as a negative here and a negative here. I pop this negative out and he makes this a plus. So the negatives are good, I assure you. Good observation, but yeah, we're safe. So 14. Yeah, this is a favorite. I like problems like this. They tend to show up on my tests. So I'm glad that you asked for this. Sigma n from 1 to infinity, tangent of 3 over n. All right. There's nothing I could hope to do algebra-wise to this because that tangent function is like a closed box. I can't open it. But one of your special limits from Calc 1, you learned that the limit as theta goes to 0 of tan theta over theta is 1. Right, just like sine x over x. No, it's actually not smaller than 3 over n. The tangent function can be well approximated by its inside near 0, but it's not strictly smaller than. Tangent is actually a little bit larger than. So I can't use a DCT, but I can use an LCT. In other words, this limit is the same as saying lim n to infinity tan 3 over n divided by 3 over n equals 1. Because as n goes to infinity, 3 over n goes to 0. So sending theta to 0 in this first guy is the same as sending n to infinity in this guy, because this goes to 0 and this goes to 0, and they go at the same speed. Right, well, if I wanted to show that this limit is 1, I would get there with L'Hopital's rule. Yeah, good. But the reason I'm writing this down is because it tells us what to do with this series, not because this gives me any information directly about the series, but it says that, i.e., tan 3 over n is very, very similar to 3 over n for large n. So I'm going to run a limit comparison test. Well, so Caesar asks, can I do this with sine and cosine also? Who else has limits like this? Just sine, right? Not cosine. So if you have a sine of something going to 0 or a tangent of something going to 0, you should limit compare against the inside. That's the idea. So we've done this for a sine function before. We haven't done it for a tan function before, and those are the only two that it works well. Cosine, this would not be necessary. If that was cosine of 3 over n, then the test for divergence would work because cosine of 0 is 1, not 0. So I'm going to pick Bn equal to 3 over n, and then calculate C as the limit n to infinity an over Bn, which is the limit as n goes to infinity, tan 3 over n divided by 3 over n. That looks like 0 over 0, so one run of L'Hopital's rule will do the job. I get secant squared of 3 over n times the derivative of 3 over n, which is negative 3 over n squared. And again, I'm kind of abusing the derivative thing here, writing it with n's, but that's okay. These cancel, and you get secant squared of 3 over infinity is 0. Secant of 0 is 1, so that's 1 squared, which is 1. Since c equals 1 is positive and finite, sigma tan 3 over n does the same thing as regular old sigma 3 over n. This is a divergent p-series. I should say this is divergent because it's equal to 3 times sigma 1 over n, a multiple of a divergent p-series with p equal to 1, which is not bigger than 1. Therefore, by LCT, sigma tan 3 over n summed from 1 to infinity diverges also. So that's the attack here. So yeah, if you see a series with tangent of some stuff that goes to 0 or sine of some stuff that goes to 0, you should limit compare against the inside. Because you've got this special limit, and then there's another one. The other one is lim theta to 0 sine theta over theta equals 1. So in other words, sine theta and tan theta both behave a lot like their insides as long as their insides are close to 0. As n gets large, 3 over n does get close to 0. So the tangent of 3 over n is a lot like 3 over n itself. And that's the hint that tells me to limit compare with Bn equal to 3 over n. Some L'Hopital's rule, and then you just write down your conclusion. This is a hard class. There's a lot going on here. There's a lot to remember. If you're feeling frightened, then there are 2 things I can recommend. First, make some flashcards with all the theorems and all the convergence tests. Make sure you can say limit comparison test, and then tell me exactly what the hypotheses are. If sigma an and sigma bn are series with positive terms and C is the limit an over bn is positive and finite, then sigma an and sigma bn do the same thing. Make sure you can do that for every single convergence test. The series here does not diverge because the limit came out to 1. Because the limit came out to 1, which is positive and finite, the two series do the same thing. That's how LCT finishes. So because that limit was 1, these two series do the same thing. And then I can conclude that my series diverges because I know that this series diverges. So I say Joe goes the same place as Sally, Sally goes to divergent land, so Joe goes to divergent land. That's the way it goes. If the limit you get from limit comparison test is not both positive and finite, then the test is inconclusive. Yes. So if this limit came out to -1, we're like, oh, fuck, try something else. If that limit came out to 0, we'd be like, ah, fuck, try something else, because 0 is not positive. If that limit came out to infinity, again, not finite. So in all those cases would be inconclusive. So again, if you're feeling nervous, make some flashcards. Make sure you know the theorems dead cold. Hypotheses, conclusion. That will get you through the true, false, and multiple choice stuff on the test. And it will also put you in a good position to earn some partial credit on the problems just by making sure you write down the correct stuff. Yeah, feel free to rock Quizlet. Quizlet's really good for this sort of memorization things. My normal suggestion is you should work lots of problems. Work lots of problems until the things become second nature. But we are very much in the last minute here. So if you are still in a place where you don't know those convergence tests cold, then it's time to make some flashcards. Check out the Quizlet. Quizlet's really good for that. I imagine you would want to hit Nicholas up for those. I have not reviewed this Quizlet. I don't know shit about it. So you might want to double check things. The test is this Friday. All right, we've been talking about this for a while. The test is this Friday during class time. All right, so the test is Friday at 11:30. Just like for exam 1, I'll leave a full 2.5 hour window open. So you can take it anytime between 11:30 and like 2. I'm sorry, 11:30 and like 1. But you'll have a 75-minute time limit. And I strongly recommend you start the test right at 11:30. That way, if something goes wrong, you'll have as much time as you can to fix issues. So the test is Friday at our normal class time, 11:30 a.m. It is a 75-minute test. It will be leaning a little bit more towards free response than the multiple choice true false because I got some feedback from students last time requesting that. I'm happy to do that. Extra time on the test. I mean, if you have accommodations through the DRC, hopefully you've already set those up. If you are entitled to those but have not set them up, then you can reach out to them. But otherwise, I really can't offer extra time. I will write the test to be a 75-minute test. So I'm not going to give you 3 problems that each take an hour. That would be horrible, right? So there will be somewhere around 7 or 8 true, false, and multiple choice questions, somewhere around 5 free response questions, 5 or 6 free response questions. And most of the free response questions will be very fast if you know what you're doing. That's the idea. So I won't give you anything like that n over square root of n cubed plus 2 problem that we had at the start, where even if you know what you're doing, it takes forever. So the free response questions will be such that if you know your theorems and you have practiced the problems, you'll see right away what to do, and they should take no more than 5-6 minutes each to complete, something like that. I am trying to be sensitive to the time stuff. That's one of the reasons I'm including more free response questions so you don't burn time on multiple choice that you then either just get right or wrong. So my advice is to go through and look at all the problems, solve the ones you know how to solve right away, flag the ones that are hard, and come back and solve the ones that you feel like you have some idea of what to do, or at least get started on them. If you get stuck, move on to the next. And then after you've gone through the test twice in that fashion, then you go through one at a time and just grind until you get them. Okay, that is it. So I'm going to go ahead and switch over to my office hour now. I need to use the bathroom and get some water, all that stuff, but then I'll be there so we can work more problems if you like. And if you have questions after the office hour, if you're unable to come to this office hour, just shoot me an email or a Canvas message and I'll do my best to get you a good answer before the test. Remember to work on the study guide. You can always send me pictures of your study guide work for critiques. That's a really good idea coming into this test. And I'll be really diligent with my email over the next couple days so you get fast responses. All right, so I'm gonna head out. I will see you guys either in office hours or next Monday after the test. Remember, your test is Friday, this Friday, 11:30. All right, bye guys.